So now we start large format machining. This week is making big stuff. Next week we then do embedded programming and we learn how to program the boards you just made. The assignment this week is one of my favorite assignments for the class. It makes something big. You'll each get in US imperial units, a 4-foot by 8-foot sheet of plywood with a large format machine tool. And the goal is to make something big. And so a really dramatic example of this week's assignment is a colleague at MIT, Larry Sass, used a ShopBot, the large format machine most of you will be using. And he did this week's homework assignment, but he kept 2 ShopBots running for about a week, cutting out pieces. And then at the Museum of Modern Art in New York City, did this beautiful, completely snapped together house. So the only tool is a rubber mallet. And then you assemble the parts as they're produced. And then when you're done, you get this house. So you don't need to make a whole house this week, but that's an inspiration for what's possible. And I'll come back to this in a little bit, but it doesn't have to be flat. Here are some beautiful examples of homework for this week. These are making flexural structures. There's another version of what you can do this week. And one more really nice version of what you can do this week is if I go to the MIT class a year ago, for this week, Sam Kalish, who's one of my current students at MIT, he used this class to make the structural frame for this kayak. And then in a later class, he skinned the kayak. And so this was his interpretation of the homework assignment for this week. Okay. So first is machines. So this week is on computer-controlled cutting, but in 3 dimensions and with bigger forces, bigger tools. So the little milling machine you're using, the Medela, can do more than 2-dimensional circuits. It's a 3-dimensional milling machine. And Roland's site shows lots of examples of what you can do with that. We'll be using that when we do tooling, for example, for molding and casting. The most common tool you'll be using for most of you is this or something similar to this. So the ShopBot, these cost about $20,000, and it's a 4-foot by 8-foot by 1-foot volume machine tool. And it's not just a router, it's a real 3-axis milling machine. So it's got enough torque to cut with substantial forces, cuts in 3 dimensions. These are developed by a dear colleague who was a neurobiologist at Duke and built these in his garage, and these ended up taking over his life. So they're very reasonably priced for what they do. So for many of you, the ShopBot's the most common tool. Just to mention a few machines, in my shop at CBA, one of the machines I have is, sorry, let me move the window. And let me get to my class notes. We have this machine that's a large format 5-axis that's dramatically stiffer than the ShopBot. It lets you cut much harder materials much faster. But one of these costs about $100K, as much as a Fab Lab. Another machine we have is this, which is a version of the ShopBot with 2 extra degrees of freedom. So along with 3D, there's two extra degrees of freedom in the head for full 5-axis machining. From ShopBot, that cost about $40K. And in addition to the cost, there's another limitation. I'm waiting to get the attention of this. Okay. The toolpath generation is much more complex for 5-axis than 3-axis machining. Another large format machine tool we have is a computer controlled lathe that is less well used. Then another large format tool is a water jet cutter. One of these costs as much as a Fab Lab. These are about $100K. Cuts with a supersonic jet of water with a garnet abrasive. It's not a full 3-axis tool. It's 2-axis plus you can tilt. What's nice about these is you can cut 6-inch steel or glass or ceramic, materials that you can't machine, you can cut ballistically. And so these have been rapidly growing, displacing a lot of machining. But along with the cost, a big limitation on them is they consume a lot of garnet, the abrasive, and then there's a lot of removal of garnet. And so these really need a lot of support and a good supply chain. They're not low-cost machines to run. And finally, there's been some work in the machines that make on making bigger machines. Kenny Chung, when he was here, who did the digital composites, made this, which was insert molding with cement to start prototyping a DIY machine with a larger bed. Nothing's happened recently on this, but this would be a great direction to develop for machines that make machines, but starting to look at doing it on larger scale. But focus for most of you will be a ShopBot or equivalent, large format machine tool. Next comes the material. One of the most common materials we use and is rigid building insulation. And so one of the, in the US vendors is Home Depot. And so if you start with and then rigid. So here's, it's 2 foot by 8 foot by 2 inches for about $20. This is the rigid insulation, rigid foam used for insulating buildings. But it's a great material to use on these large format machine tools. It machines extremely quickly. The surface finish isn't very good because of the granular foam structure, but there's a few ways you can improve the surface finish. One is you paint it with a gesso, the same material you use to seal a canvas, and then sand it. Or another is you can just use a heat gun and melt it back a little bit. Both of those help seal the surface. And then once you mill the foam, you can either paint that and use that as a finished object, or we'll see you can use it as tooling for casting. So you can, for example, cast concrete in it. Or a really important process is you lay up composites. And so for the wind tunnel project, you can mill the foam to make the shape of the tooling. Then you lay up the composite in the foam and use that to make tooling. So that's one really nice material.
Hey, Neil.
Yep.
Hi, this is Matt in California. A couple quick notes on this. I've been spending some time with a machine called a 2-bot, a number 2 and then BOT, and been using this EPS from Home Depot. So one of the things that I've learned is some of the sheets from Home Depot have cuts in them, which messes things up. So that's one note. Another material in addition to Odesso that I'm going to be trying is a stuff called Styro Spray 1000.
Huh.
And I'll send out an email about this, and it creates some sort of harder plastic shell on the foam. I guess they use it in floats a lot in parades.
Yeah. I've never seen that. Give yourself a week, play with it, and then next week in class report back on that.
Sounds good.
Yeah, interesting.
Neil?
Yep.
This is Jonathan Schmidt from Meadowbrook. One thing I found too with that foam is our local fire department won't actually allow us to have it because they say it's a flammable fire hazard. So we're looking for another cheap material that will work, but that's one problem we've come up with that rigid foam.
Yeah, here's why I'm quite surprised. The shop I run at MIT is thoroughly supervised by MIT's Environmental Health and Safety, and the fire department comes through here and reviews everything that we do. So, you know, not the Fab Lab, but the MIT shop is as supervised as a shop can be, and that's never been raised as a concern here by Cambridge Fire Department.
We have an especially cranky fire department, so perhaps, I don't know, but I might try to find some information to educate them a little bit on how it is safe.
Yeah, you know, if you send me a note, I can introduce my shop manager here, who could introduce our environmental health and safety. That just sounds wrong. No, yeah, I mean, no, in fact, here's why I know it's wrong. This is in the buildings all around us. If this was a fire hazard, it couldn't be a fire hazard, or else all our buildings would be fire hazards.
Yeah, I wasn't able to talk to them directly, but they said that the problem is if it's not lined with paper, if it's just bare, then it's an issue. But if it were to be bagged,
it sounds crazy.
Yeah.
Hey Neil, this is Marcus.
Yep. Sorry, Marcus, I didn't mean to step on you. I just wanted to add real quick. I think it is a disconnect with the fire thing. One aspect I wanted to add is I've been doing a bunch of R&D with a mushroom foam company called Ecovative. And what they do is they grow packaging material out of they won't tell me yet. I haven't signed their NDA, but it's some sort of soupy stuff made with sawdust and mushroom cilia, and they actually grow it to the size of the packaging for sustainable packaging. And I've been working with them to create sheets of this stuff to actually mill.
Yeah, I was intrigued, but I didn't get past. They're a bit secretive, and I couldn't get information. So
yeah, they're not real forthcoming, and so I'm trying to work past that.
Yeah. Okay, Marcus.
Yeah, just another voice here in Maine at our school. We're in the same situation with the foam stuff. We're not allowed to even have it on campus. So just if those guys have got a cranky fire department, I guess we've got maybe the same strain of crankiness virus.
You know what? If it's two of you, let me. I'll send a note to my shop manager here and our health and safety people to see if I can get backup for that. Again,
that'd be great. Thanks.
First I've ever heard of that. Okay, so foam, and then we get to plywood. So if we go back to Home Depot, there's veneer plywood, where you peel off veneers of wood and laminate them, that we generally don't use. That's much more expensive. There's a couple kinds of plywood that we make a lot of use of. So one is medium density fiberboard. I don't know if Home Depot lists these this way. So here's MDF. Medium density fiber, or MDF, is wood fibers in a polymer matrix. What's bad about it is it's relatively weak. The fibers are short, and so if you load it, they just kind of pull apart, and it's fairly heavy. What's good about it is it's very uniform internally. So it's more expensive and heavier than the foam, but it machines beautifully with a beautiful surface finish. It's the most uniform of these materials. And so it's a great choice for something a bit more expensive for making tooling. And then one note on fiberboard, there's a resin matrix, and some of the resins used are nasty. So the famous FEMA trailers that made people sick had MDF with a toxic resin. But there are friendlier MDFs that have less nasty resins. So that's MDF.
Neil.
Yep.
How would you know what kind of MDF you have?
They're labeled. The good ones are labeled like green or friendly. They have words to that effect.
So if you got an unlabeled one,
it's probably nasty.
Okay. And
good ones are labeled in some way.
One note on machining MDF and working with MDF.
Yep.
It's basically dangerous.
Say it again?
It's basically dangerous because of the fine dust.
Yeah. In fact, I don't have a good note on this. Let me add that. Any of these, you want to have very good dust collection. That is, you're machining, you're making dust that you don't want to breathe. You want to have active dust collection. Now,
yeah.
a really nice...
Even on sanding, sorry.
Sorry?
Even when you're sanding it, you want to do that either outside or under good ventilation.
Yeah. So, MDO is a little bit harder to find, but a really nice choice. This is used often, for example, for billboard signs. MDO is a plywood core with an MDF layer on top. And so it's kind of the best of both, where it has a very smooth top surface from the MDF, but the MDF isn't the structural material. Natural wood, wood is a natural composite, so it has a plywood core with an MDF overlay that's smooth. And so MDO is a really nice compromise. And then finally, something we make a use of a lot of that's unloved but cheap and cheerful. Comment? No. Konstantin?
Yep.
Yeah, comment? Yeah, comment? Otherwise, mute, thank you. This is now OSB, Oriented Strand Board. This is the cheapest of all of them. So here's 4 feet by 8 foot for $15. OSB is, you take what's left over after the good wood, just the chunks, and you smush the chunks together. So OSB is by far the cheapest. This is used for like boarding up buildings. But it's got reasonably good mechanical properties. It doesn't have a great surface finish, but you can sand it and seal it and do things like that. And it's by far the cheapest. And it's also somewhat friendly in that you're using every last bit of wood from the tree. And it has much less resin than MDF because you have real wood chunks. The wood is actually held together with the natural resins, and then you're just sticking them together. And so especially for something, a learning week like this, we use a lot of OSB. It's sort of like the cardboard of plywood, the thing that's cheap and cheerful you can use a lot of before you move to fancier wood. You can mill aluminum on a shop bot. It's relatively slow, but you can. It's happier on a Witterjet cutter. Lexan or polycarbonate, you can't laser cut it unless you have a kilowatt laser, but that machines nicely. You can machine that. And then finally, you can't mill glass or ceramic, but that's another nice use of Witterjet cutting. Glass is a really interesting prototyping material that Witterjet cuts beautifully. Vendors.
Yes.
Yep.
Can you cut Korean on Shopbot?
I've never done it, but I believe you can. You'd slow it down a bit, but I believe that would cut without trouble.
Okay, thanks.
Yeah. McMaster Car in the U.S. stocks all of this, but I don't recommend it. It's expensive. In most parts of the world, there's local distributors. So locally around Boston, there's Admiral Metals for metals. There's Bolter Plywood, Sterrett, Beacon Sales for lumbers. These are yards that have these things, and each of you will have something like that in the vicinity. It's typically hard to get a predictable supply of any one of these, but if you go to these lumber yards, you buy what they happen to have around. And often what we would consider a project, they would consider scrap. That when they do a big order for a big building, they would go through a lot of this, and then there's some leftovers that are of the size we would use for one of these projects. And so it's a good idea to go visit your local lumber yard, both to see what they have, but also to see what they happen to have on hand then. And you can get great deals on the scraps left over from the bigger project. So pick out your stock. Next comes tooling. In the standard inventory for Fab Labs, there's a section from Onsrud where this is the tooling we've been putting in the Fab Lab. And you'll see there's much more here. For the Modella, you just use the 1/64th and the 1/32nd, and that's it. For large format machining, there's much more to say about tooling. So the first distinction is drills versus mills. So a drill has a tip with spiral flutes and cuts down. An end mill has either a flat or a round bottom, and it's designed to cut horizontally. So mills go horizontally, drills go vertically. Now, there are center cutting end mills. If you look at the tip of an end mill, if the flutes go all the way through, that's not center cutting. But if on the tip of the end mill, if there's a gap between the tips, then that leaves room for the chips to be cleared. So a center cutting end mill can go down as well as horizontally, although it doesn't cut down as efficiently as a drill does. And so largely we stick with center cutting end mills so that you can go both vertically and horizontally. Then there's the number of flutes. So a 2-flute end mill has 2 flutes spiraling down, 3, 4, 5, even 6 flutes. 2 flutes is good for chip clearing. You get mass out more easily. 4 flutes is good for surface finish. You're making more small cuts than fewer big cuts. And so there's a trade-off with if you want to roughly remove a lot of material or slowly remove more material. There's coatings. So typically we use carbide tools with a ceramic coating that cost a little bit more but significantly extends tool life. Then another very important attribute for this week is the flutes can either go clockwise or counterclockwise. And that corresponds to up versus down cut. So far in the milling, we've only been using up cut, so it pulls up. But when you mill with up cut, it's trying to pull the stock up. A down cut has better holding because the cutting force is actually pushing the stock into the bed, but it is the problem that you have to get the chips out. So for down cutting to work, you want to mill all the way through and have a path for the chips to go out the bottom. Now, if you upcut, the bottom surface is smooth, but the top is rough. If you downcut, the top is smooth, but the bottom's rough. There's center cutting tools, and these, a center cutting tool has flutes going one way, meeting flutes going the other way in the middle of the tool. And so what it's doing is it's pulling the chips into the middle of your stock. And so that has nice surface finish on the top and bottom, but the chips have nowhere to go, and these are worse for chip clearing. And finally, you can have a flat end tool or a ball end tool. The flat end tool makes flat surfaces. The ball end tool is better for undulating surfaces because it doesn't leave steps behind. Although that distinction matters a little bit less if you're doing full 3-axis machining, where the tool is making full 3-dimensional paths. And so these choices vary very much on the application of what you're making. And as an example, in the Jonathan Ward, who developed the first snap-together MTM machine, and in fact, I'm missing a material. I'll add one more material. This is HDPE, high-density polyethylene. This is used to make cutting boards. HDPE is another nice material. It machines beautifully. So here, let me go to McMaster and then search for HDPE. And then we want sheets. These are HDPE sheets in all different sizes. It's never cheapest from a place like McMaster, but it's a convenient place to buy it. There are plastic vendors that are cheaper. HDPE machines beautifully, is a strong material. It makes these nice flexural connections. And for milling this, Jonathan ended up settling on one flute upcut. So just a single flute that removes a lot of material at upcut. And with the one flute upcut in HDPE, it's almost like laser cutting. You can zip through it really quickly because you're removing so much material so quickly from it. So that machines beautifully. So to do this week's assignment, there isn't a single tool you'll use. The tool choice depends on the project and on the material. Next is speeds and feeds. On the milling, there was just a PCBs. There's a default setting, and you never had to change that. For machining in general, it's speeds and feeds are how fast you go and how much each step does. This is a wonderful Bible, Machinery's Handbook. It's 100 years old, and it's got pages and pages and pages on that. I really recommend flipping through a copy. So there's a couple general principles. Chip load is how much material is removed in each pass of a flute. And so it's the feed rate in inches per minute divided by rounds per minute times the number of flutes. And a number between 1 and 10 mils is a typical number for the chip load for how much one flute should be removing in one pass. Then the cut depth is how far you go down between passes. And there a typical number is a cut depth roughly on the order of the diameter of the tool. Then the step over is how much adjacent passes overlap. If there's no step over at all, you're machining most quickly, but you get little seams at the edges. A step over about a half is a reasonable number where there's no seams between the passes, but you're wasting some time. And you can even use much finer step over if you're doing finishing passes for a good finish. Lubricants do two things. Lubricants help reduce friction, and they have a very important job in heat transfer. They help cool the tool and the stock. Wood doesn't need it, or acrylic. If you machine aluminum on the ShopBot, for example, then you need a lubricant. And a typical one we use is an oil emulsion that you spray on it. Generally, the symptom that you need a lubricant is it's getting very hot. A special kind of machining is abrasive machining. Here I'm linking to just an abrasive grains. You can machine hard material like glass. You can't do it quickly, but what you can do is you make a slurry of an abrasive paste. And then you have a tool that doesn't have flutes, just has a shank with a shape, and you spin it, and the spinning tool stirs the abrasive and grinds away the material. And so you can use that to do hard materials by machining with an abrasive, generally for fairly fine features, not for big things. Okay. Next comes fixturing. This is a big subject of how you hold your stock down. So one way to fixture is you just clamp it, and that works for projects that aren't too big. Problems with just fixturing with clamps, one is when you, so typically you'll have a sacrificial underlay that's been milled to be flat, and then you have your stock on top. If you clamp it from the side, that does a couple things. One is the material slightly bows, typically. It's not quite flat. And the other is you're not holding in the middle. And so if you're cutting out a shape in the middle, it can wobble because it's not held from the sides. I'd say for big machining, the most common way we fixture is with a cordless drill and fine wood screws. So what you do is you have a box of wood screws. You pick places where the milling bit isn't going to go, because you don't want to mill through the wood screw. With the cordless drill, you just drive a bunch of wood screws in, and it just takes a moment to screw it into the underlay. And what's nice about that is it distributes the holding force, and then when you're done, you pop them out. That's really quick, and that works really well for holding. You can make a vacuum bed and hold from underneath by pulling a vacuum. That sounds great. The problem with it is the vacuum beds get crudded up and lose vacuum, and you have to keep cleaning them. And so these are used in production in shops where you need quick turns. They work less well in prototyping shops because you need to tend the vacuum bed, but that is an option. If you want to mill with more than one side, part of fixturing is tabs. So you mill part of your part, but you leave tabs holding it behind so it stays connected to the rest of the stock rather than wandering around. For machining that doesn't have large forces, like water jet cutting, you can just use weights as vertical force. Something else we make a lot of use of is an adhesive. So for example, a glue gun. So if you want to mill a foam block, something we'll do is you put it down and you just run a glue gun bead around it because the forces aren't that large, and you just crack off the glue gun when it's done. And finally, for really complex machining, a technique is you take what you're going to mill and you encapsulate the whole thing in a machinable wax or a low-temp metal, and then you mill it, and then you melt away the encapsulant. And that's a really neat way to fixture for making very, very complex shapes. Okay, so that's fixturing. Next is a note on flexures. The stock you'll be cutting starts flat, but the project doesn't need to be flat. And there really isn't a single design tool, but these are some examples. Down here at the bottom, this is Vladimir from Mises in Moscow. And you can see this beautiful curving structure for this rocker. The stool, I think, was made in Providence. I don't recall who did that one. This is really nicely done, milling these grooves to fold it. And so this is a flexure cutting all the way through. This is a flexure not cutting all the way through. But these are examples of, you can start with 2D stock, but by milling in flexures, you can make it fold into a three-dimensional structure.